Hello everyone, in this video I would like to show us examples on equilibrium constant problems. Consider this reaction that we have here with this reactant iodine and chlorine gas with the equilibrium constant 81.9. Given the partial pressure of these reactants and gases. So the question says, is this reaction mixture at equilibrium? If not, which direction will the reaction proceed? In order to solve this problem, we need to find our reaction quotient and compare this reaction quotient with our equilibrium constant. So our reaction quotient will be Qp because we have the partial pressure of reactants and products. So our Kp is gonna be the partial pressure of Cl2 over the partial pressure of iodine gas times the partial pressure of chlorine gas. We have this to be, which is gonna be 0.355 atmosphere squared over for iodine molecule is gonna be this 0.114 atmosphere times for chlorine gas we have this 0.102. When we plug this into our calculator, it gives us 10.8. So we have our QP to be 10.8. So the next thing we need to do is to compare our QP and K. So compare QP to K. The K is 81.9, so we say this is 10.8, 81.9. So in this case, QP is less than our KP. Because our QP is less than KP, it implies that the reaction will proceed to the right. Proceed to the right. It means that the right is where we find the products. So it's going to proceed to the right where we have the product. So this is another example for this reaction. The Kc is 2.0. At 1000 degrees C, we have the concentration of reactant to be 0.255 and the two products CO2 is unknown and we have the CF4 to be 0.118. What is the equilibrium constant of our CO2? So we are looking equilibrium concentration. So we are looking for equilibrium concentration for CO2. So the first thing we need to do is to write a relationship for the expression for our reaction. So it's going to be our Kc, which is going to be the product over the concentration of the product over the reactant. In this case, we're going to have our CO2 concentration of this and CF4 over COF2 squared from the reaction. So we are actually looking for the CO2 concentration. We can rearrange this equation so that we can get our CO2. So we can say CO2 concentration is gonna be Kc into COF2 squared over CF4. So we can plug in all those values that we have here. Our Kc is 2.0, it's going to be 2 times our COF2 is 0.255. We're going to put it squared raised to power 2 over CF4 is 0.118 molar. Right. So when we plug this into our calculator, we should have 1.10 molar. So our concentration for CO2 is 1.10 molar. Okay. So another example we want to consider is this. Given this reaction, where we have CO plus 2 molecules of hydrogen gas given this product. So this reaction contains concentration of CO to be 0.5 and hydrogen to be 1. At equilibrium, the concentration of CO is found to be 0.15 mol. What is the value of equilibrium constant? So in this case, we are looking for the equilibrium constant. For us to find this, we need to find the equilibrium concentration of the reactants and the product. So we need to set up an ICE table. We need to prepare an ICE table using the ballast equation as a guide and then showing the known initial concentration and equilibrium concentration. So using this as a guide, so we're going to have our ICE table this way. Okay, okay. So ICE initial, change, and equilibrium. So we have CO as reactant and hydrogen as reactant. And our product is CH3OH. Set it up this way. Initial concentration of our CO is 0.5 and hydrogen is 1.0 and this is 0, which is our product. So the change in this is gonna be X. Our change is X, unknown. So because this is a reactant, we're going to have negative X. Reactants are consumed. And for our hydrogen, it's going to be X. Well, going by the equation, we have 2 moles of hydrogen, so we have 2x, negative 2x. We also have this to be positive x because that is our product. At equilibrium, our CO was given to be 0.15, so we're going to plug it in here. So we can use that to find the equilibrium concentration for hydrogen and oxygen. So let's take this. Let's take this to find our x. So we're going to have 0.5 plus negative x to give us 0.15. If you solve this is going to give us our x to be 0.35. So if you plug in all this 0.35 into this place, this is going to be negative 0.35. Here, this is going to be negative 0.7, and this is going to be positive 0.35. Right. So we can make it to look clearer by rewriting this. So it's going to be ICE again. So this is still going to be our CO, hydrogen, and our C3, CH3OH. So this is still going to be 0.5, 1.00, and this is going to be negative 0.35, and this is 0.15, and this is going to be negative 0.7. When we subtract 1 from 0.1 plus negative 0.7, it's going to give us 0.3. And this is going to be positive 0.35 plus 0. When we add this together, it gives us 0.35. This becomes our equilibrium concentration. Now, we can find our equilibrium constant, K, for this. So we can write the equilibrium constant expression for this guy. So which is going to be Kc gonna be we're gonna use our equation as a guide. As usual, our product is CH3 0OH over, we have the reactants, which is gonna be CO, and hydrogen, and our hydrogen is gonna be to power 2, right? So let's plug in this equilibrium concentration into our Kc. So it's going to be 0.35 into our CO is going to be 0.15 times hydrogen, which is going to be 0.3 squared raised to power 2. If you plug this into our calculator, our Kc is going to be 26. Next, similar problem. For this reaction, right? So we have the concentration of our reactant to be 0.115 molar. At equilibrium, it contains this molar of C2H2, what is equilibrium constant? So what we're gonna do is, again, we're gonna use the balanced equation as a guide, and we prepare our ICE table this way. We have our ICE, and it's gonna be, in this case, we have only one reactant, which is CH4, and we have two products, C2H2 and hydrogen. Right. So we have the initial concentration of CH4 to be 0.115, and of course this is our product, is 0 initially, and we have our x to be, our change to be negative x, but in the question our moles of CH4 is 2, so we have negative 2x. And this is going to be positive x, still 1, because in this equation we have 1 mole. And for our hydrogen, it's still going to be positive x, but we have 3 moles of x, so it's positive 3x, the product. At equilibrium, this, our C2H2 at equilibrium is 0.035. So, as usual, we can find our x using this expression here, right? So that becomes uh, 0 plus x equals to 0.035. Our x is still 0.035. So if this is 0.035, we can plug in this into this expression. So we replace this with 0.035, 0.035. We plug it in also here, we plug it in here. So when we plug this value of x into this expression, so we're gonna have a new, value. So we have our ICE table to be, this is still CH4, and the C2H2, and our hydrogen, right? So this becomes still 0.115, and when we multiply these two by 0.03, give us negative 0.07, and this is gonna be, this is 0 and 0, this is gonna be positive 0.035, and this is gonna give us positive, when we multiply this by 3, it's gonna give us positive 0.105. So we can find this. This is gonna be 0.115 minus this, so which gives us 0.045, and this is of course 0.035, and this is gonna give us 0.105. These are the equilibrium concentration for our reactants and our products. So the next thing we do is we find the equilibrium expression. So our K is going to be the concentration of hydrogen. And remember, our hydrogen is in our original equation, hydrogen is 3, so we're going to put it this way. And C2H2 over C8 4 raised to the power 2. Okay, so we just plug in these values that we have at equilibrium concentration, which is C. So our Kc is going to be 0.105 times 0.035 over 0.045 squared. Okay, so when we plug this into our calculator, it's going to give us 0.02. So that gives us the value of our equilibrium constant expression for that. I hope this helps us in solving more problems. Thanks for watching.